Pointer. Well, hi everyone. I'm delighted to be here, all the way over from Ireland. Indeed. Big shout out to Nadir and the team who have shown extraordinary leadership to pull this all together. It's a truly great session. And delighted to be part of it. So yeah, I'm going to talk about avoiding chronic disease. I'm going to have an insulin theme, but then in the latter 30 minutes, I'm going to go through some of the LDL research I've been doing to go a little deeper into why high particle counts could be a problem. You know, get some more context around LDL. So hopefully you'll find it interesting. So first, the reason I'm actually doing any of this in the last couple of years is my boss, who has a huge passion, and he explains it here pretty well, I think. No.
If I can save one life, if I can help many people have the same opportunity as I have, why should somebody like myself have this opportunity that's not given to others? And that's true every day, every single day.
And that is David Bobbitt, one of Ireland's most successful entrepreneurs, business owners. He owns and runs a $700 million business. And he had a near-death experience when he got a calcium scan 6 years ago. All his blood metrics looked great. He was super fit and running, looks like he does now. And he got an enormous score, and he had to get a lot of changes brought into his life. But he has now stabilized his disease based on that wake-up call. And he is spending millions to let everyone else have the same chance as you saw there. So I'm working on behalf of his charity, Heart Disease Awareness. There's no financial interests here whatsoever. It's philanthropy, no ties to the cardiac imaging business. So I am later in the talk going to get into some pretty juicy stuff around how your arteries fall apart. But first we're going to go through that crucial scan. So, and we have a saying in engineering, if you don't measure it, it don't get fixed. So it's very important to measure the correct things that give you the most information, the most bang for the buck. So here's the calcium scan, and you see on the left a guy, it's actually Dr. Jeff Gerber, who has 0 calcium in his coronary arteries. So that gives you a 0 score, and it bodes extremely well for your future because it shows you have no atherosclerotic disease worth noting built up in your body at middle age. The person on the right has a lot of chalk in there, and they have had the inflammatory disease of atherosclerosis burning away, and they've built up a lot of calcium, which the body brings in to try and strengthen the arteries. So it's a canary in the coal mine. And all US presidents and astronauts must take this scan because it's that powerful. It's the bottom line in finding out your risk. So unsurprisingly, the top guys have to get it. To give you an idea, here's a study. All the studies say the same thing, essentially. Here we have people with low scores, 1.4 to 4% cardiac events in the following 10 years. If you move up to higher scores, you see you go all the way up to 37% events. So that's nearly a 20 times higher rate of events for having a high score. So if you have a high blood pressure, it might be 1.8 times more likely. But the risk factors in your blood are very indirect. This is directly looking at the disease. That's a $100 5-minute scan. Here's one for patients actually, and how many died after the 12-year period. As you can see, with a very low score, it's not 0, but only 0.6 or 1 in 200 were dead from this patient group, which is extraordinarily low for that kind of group. It was the West Coast. You can see as the scan result got higher, you've got a huge multiplier in how many are actually checking out. And at the highest scores with massive disease being discovered by this amazing scan, you can see the vector they're going on. Nearly a quarter of those people dead after 12 years. So that's a 40 times more people dead based on very high scores. So it's an incredible scan. Oop. Now, we'll branch into LDL and some measures. How useful are they? And as you can see here in Heinz-Nixdorf, going across the bottom, we've got people who have low calcification, very low disease, all the way across to super high calcification, massive disease, right? But you'll notice that the LDL isn't much different between these dramatically different people. The guy on the left in the black shirt has very low disease, and he's got an LDL around 130s. The guy on the right has got enormous disease, LDL in the 130s. So it just illustrates that in the engineering world, we couldn't use that to predict because it's ambiguous. So we'll go into more detail later. In this study, though, blood pressure and diabetes extent certainly were linear in dose response and predicted the higher disease. No measure is perfect, but these are pretty good. And one reason is type 2 diabetes is hyperinsulinemia, insulin resistance, and most blood pressure, idiopathic, where they don't know the cause, most of that links back to hyperinsulinemia and mechanisms around that issue. So a quick study here again, we'll see can you spot the important factors. And in this study of people who had second heart attacks or did not have second heart attacks after their first one, followed for 7 years, they looked to see what's important in predicting the second heart attack, right? That might be the big one where you go down permanently. So hypertension history was a 2 times multiplier if it was high. That's pretty good. A 2 times multiplier is a reasonable factor to look at. Total cholesterol, not really significant, 1.5, and LDL wasn't significant at all. Right, so fair enough. You can draw something from that. But then they did a multivariate analysis, and all this is a mathematical analysis to try and see which factors are actually dependent on other ones and which factors are truly independently predicting. And in that analysis, the cholesterol and LDL basically fell away to nothing. And what do people think insulin values were in terms of a multiplier? 2x is good, 4x is really good, 6x would be really, really good to predict. Yeah, so 6.7x. And the paper summarized that basically, guys, we are missing out on an enormous amount of preventative care we could put into these people because no one's measuring insulin. Ironically, one of the best measures of future issues. So, one more paper, because it's not just heart disease. This is looking at all the modern chronic diseases, or most of them. And you can read there that hyperinsulinemic syndrome is broader than we think. It's not just cardiovascular, though it is that. And they got all the metabolic syndrome or insulin resistance syndrome papers out there, which had disease rates, and they sifted down to the 63 that actually measured insulin, because many of them don't. It's crazy, but they don't. And how did insulin relate to the people who got these diseases and didn't in all these studies? Well, here you are. In nearly every study, the people who got the disease were significantly higher in insulin than the people who did not get the disease. It's cross-sectional analysis. But I'll let you read through some of these conditions where insulin was a very important marker. It's way beyond cardiovascular disease. Pretty much it's the stable of modern chronic disease. 60 out of 63 studies hit home with insulin being the critical variable. And we're not measuring insulin, generally, which they said was crazy, and I'd agree. It's made more absurd when the latest data shows that around 65% of American adults over 45 are now pre-diabetic or diabetic. Now, pre-diabetic, diabetic, hyperinsulinemic, insulin resistant, a lot of words that just means one particular function. Dysregulated insulin dynamics. And you've got this 2/3 of adults have it. So is it any surprise the mess we're in? And if you used insulin measurements, you'd get more. Myself and Dr. Gerber think maybe 75 or 80. So this has been going on for decades, right? The media, the pundits, all the chatter on the internet and in the newspapers, talking about cholesterol endlessly. Meat is bad or good, fat, salt. Healthy whole grains are good for your heart, wherever they came up with that rubbish. But this fills the airwaves. I mean, it fills the airwaves for decades. But what are they missing? And they're missing, of course, the goddamn elephant in the room, right? No one's really talking about the primary problem. It's not exclusively the problem. There are many other causes. But the primary big item is not getting addressed. So I'm going to briefly do, because I need to keep time for my other stuff, a root cause diagram for chronic disease generally. And up on the left, we see excess fructose and excess glucose, especially refined carbohydrates, in excess. That does, through many mechanisms I can't go into detail on here, it drives essentially the insulin resistance syndrome over time, or metabolic syndrome, or cardiometabolic syndrome, or atherothrombotic syndrome. So many names, but it's all the same crap. So really briefly, when you take a lot of these foods, you do disrupt gut hormones. Your adipocytes, your fat cells with time become larger, the insulin signaling within them breaks down, you begin to release cytokines and many inflammatory molecules, and it leads to your whole body becoming resistant to the effects of insulin. So now you're in trouble. When you're in that trouble, you get atherogenic dyslipidemia, and this is the low HDL, the bad ratios, the high particle counts. A lot of that all comes out of this chunk. And you've got elevated glucose and insulin, which are directly going to cause oxidative stress and endothelial damage on your inner artery wall and lead to heart disease. So that's important. But we also have many other factors. It is multi-factor. So excessive omega-6 from vegetable oils and suboptimum omega-3, suboptimum magnesium, vitamin K2, some other crucial components required for the human machine. And we've got a load more stuff, but I won't go through. Even stress, lack of sleep will drive up your insulin, will drive up problems. So many things that can drive this issue of cardiovascular disease. But interestingly, a lot of these other things that directly drive the problem, a lot of them in turn drive up your insulin and your insulin resistance status. So even if it's not this system that's driving most of your issue, this system can act as a gauge of other problems, right? Insulin acts as a gauge in the body for many other issues. And I won't go through the mechanisms, but it's important. What if you have high LDL or high LDL particle numbers? We know now that the LDL from the old measurement is very weak, but the LDL particle count, counting the numbers of LDL particles, is a stronger risk measure. Well, what if you're high? And what I would generally say is, if you have some, many, or all of these issues going on, and you add in a much higher particle count in your blood, where the particles can become damaged by the issues, by all means, it's reasonable to assert that you will have an accelerating effect on any heart disease that's heading your way, right? And you will actually accelerate your problem. But it's very important that the main focus goes on the real root causes and not on this dependent path. That said, if your particle count shoots up on a new diet, you got to be really careful because it is a strong risk factor, and you need to make sure that everything else in your body is good and that this particle count won't develop to be a significant problem. So part 2, and this is the new stuff, we're going to put cholesterol and particles into some kind of context. So first I'll show the MESA study, calcification of Western people, mostly American, and this is men. And as you can see, around 50% of the population, they have very little calcification as they go from their 40s up to their 70s. So that's the half of the population who have very few cardiac events. They're the healthy guys. And then back you got the 10 or 5% of worst calcification get enormous calcification growing, as you can see in those ramps. And that's where most of the heart attacks occur. Not exclusively, but this isn't rocket science, right? The guys who are racking up the calcium are destroying their arteries. They're the ones where most events will occur. Now, we could look at another people, very different, Semaine men, very different peoples, other side of the world. But first we'd look at, before we see their calcification, we'll look at what they achieve. They achieve very low insulin, very low blood glucose, no diabetic physiology versus most of the people in the West, no hypertension, blood pressure, no central obesity, understandably, great omega-3 to omega-6 ratio in their foods. So you can kind of corral these together and say, for sure they have no metabolic syndrome, no hyperinsulinemia syndrome, right? Which is a big deal. They have none of that, not a trace. So what do they get in calcification? Well, they get this. Age-matched, like with like, humans, same as these are humans. That's what they achieve. Now, we're not going to get into their diet and stuff because they have a very special environment with many factors at play, but they achieve it. And I want you to, oh, one more. it has been said, oh, well, these are special genetic people and could have special genetics, you know, so are they unicorns? Are they the only people on the planet who can miraculously do this? And the answer is no. The Catavans with a high coconut saturated fat diet and high unprocessed carbs, in fairness, living with sun exposure and all the vitamins and minerals, they achieve this and ultra low heart disease also. And they're a different genetic people. So the human machine can, in certain circumstances, be made extremely healthy, and most of it is what goes in the mouth. This list of great things that are really important, I'm going to put a target sign on now. So I want you to think in the next 20 minutes, when you see the target sign, you'd be thinking, well, what will this list of great things that I achieve, how will that affect the cholesterol problem? And I'll show you. So many years ago, I did the cholesterol conundrum. It's on YouTube for anyone who wants to get into the detail of the cholesterol transport system and how it relates to pathology, energy delivery, and all of it. And recently I used the slides to give a rerun of this talk, and I was delighted because I didn't have to change a single slide. 5 years later, didn't have to change anything, which is good. I was happy with that. But I did raise, besides how the system worked, I raised the problems with the LDL particle count being seen as a God number. And you can see here from this study, for instance, high and middle total cholesterol over HDL ratio people, generally that means they're insulin resistant. It's a good proxy for insulin resistance. Well, for those people, going from low to high ApoB racked up their relative risk. And that makes sense. ApoB is quite a potent risk factor. However, you may have noticed that for the low ratio people who would be insulin sensitive and healthy, higher ApoB actually resulted in lower risk. So you can see this dichotomy, you might call it. You got to be very careful with ApoB particle numbers. Am I in that group or am I in this group? And not just using the ratio, but in general, using all the numbers. What group am I in? Because if you don't know what group you're in, you won't know what to do with it. So I went through a lot of papers in the last couple of months. This is my desk at home, putting it together. And I had to go to my podcast desk because I had so many papers printed out, I lost control. But a lot of paper, around 200 papers for the coming material. And they all did, in the end, dovetail together. So here is the atherosclerotic process. And what we're going to do is, we're not really, oh, sorry, it did a jump. Just a sec. Come on back, baby. Yeah. So we're not going to go through the inflammatory cascade because it's very well established, the science, and we're pretty happy with that, and it's very complex. But I will say that the target list of things you need to get right will help hugely with this inflammatory cascade. What we want to focus on is the LDL hypothesis bit, that more particles will get into your artery wall and kick off this mess. That's the LDL, that's the kernel of the LDL hypothesis. But it's not so simple as they'll just get in, gradient, diffusion, they'll just go in there. If you have more of them, more will go in. That's not true. There are 3 layers of evolutionary design systems to not have LDLs go in willy-nilly. 1, 2, 3. The first is the glycocalyx, an extraordinary structure discovered 30 years ago. And the reason they hadn't discovered it in so long, it's these blue hair-like structures, you know, made of proteins, amino acids, and glucose. The reason they didn't find it was it's destroyed the moment you take it out of the body. It disappears. So they never actually knew it was there, but they did discover it then. And it has a sieving effect, and it manages particles and platelets, and it manages what systems and what inflammatory molecules can access the endothelium, the single cell layer at the inner wall of your artery down here. So it has a very important function that no one knew about. Then you've got the endothelial cells themselves. It's a single layer of cells locked together with tight junctions, and that really is the barrier to your artery wall. But then you've got the proteoglycans, which again are sugar-based structures that can trap LDL and other particles, hold them, oxidize them, get them engulfed, taken away to be dealt with, right? And if you overload them, you're probably going to have a problem, right? You're not going to be able to take them all away and manage them. You're going to get a buildup of inflammation. So they're the 3 layers. 1, 2, 3. But what we really want to know is what governs or determines or mediates or decides how this 3-layer leakage goes ahead. You could have very little leakage across the 3 layers, or you could have a hell of a lot. What decides that? Because that's a massive question. If you have higher LDL numbers, you've got to know what state this is in. That's fair. So the glycocalyx, let's take a look. Here it is in a high-resolution electron microscope picture, and it's basically like little hairs, as you can see there. And it keeps the inside surface slick, it protects the endothelial cells. The strands, believe it or not, move in the blood flow, and they act as mechanosensors, and they actually trigger nitric oxide release from endothelial cells based on how they sway in the blood flow, and a million things more. But I just thought I'd give you a feeling. This stuff, evolution wasn't messing around when it designed this layer, put it that way. Here's a paper with a great title I got during my couple of weeks. Arterial glycocalyx dysfunction is the first step in the atherothrombotic process. Wow, that's a strong statement, and it was a great paper, and they made a lot of cases for this. So not the first step that LDL wanders across, you know, and opens a door it shouldn't and finds itself in the wrong room. No, no, no. This is the first step, they would say. So here's a group who are developing things to help the glycocalyx. I have no connections to them. The effect of a high-carb meal. Here's your normal glycocalyx. 2 hours later, 4 and 6 hours later. And these are actual, you know, scans taken. That's what happens. And particularly hyperglycemia and high sugar has been shown to damage it. You know, if your blood sugar levels are nominal, the glycocalyx is happy. It's actually not so happy with really low glucose. It's slightly not so happy. It likes glucose there, but if you bring up the glucose a little high, suddenly it doesn't like it. So that's the kind of relationship. Body takes 8 to 12 hours to recover this situation, and these guys have scanned real humans, 8 to 12 hours. But most people are going to dump another, you know, pound of carby junk in on top of themselves after 3 or 4 hours, right? Everyone's eating all the time, and they're eating sad diets. So how is it ever going to recover? Here it is shown in beautiful health. You can see the glycocalyx strands there, and there's an outer barrier area they've more recently discovered. And it keeps the red blood cells and platelets and other elements, as I said, away from the wall of your artery. Oh, here's one in a rotten state. So you've been chugging Coca-Cola or smoking cigarettes or whatever you've been doing, right? And as we can see here, the LDLs have much more access to the endothelium, the LDL particles. This group did a great experiment. They said, well, what if we damage it in the lab, carefully damage it? What will happen? The rate of LDL internalization into the endothelial cells. How much bigger will it get if we damage this puppy? So they damaged it with neuroamidase, and they got 10 times more LDL getting into the endothelial cell. And that was impressive. But then they went for gold, and they said, hey, what if we hit it with like cationized copper or ferritin? What if we really kill it? So they did. They used ferritin, and they got it down and measured to 5% of its previous thickness. And they said, right, this is really stripped. And they got 20 times the LDL getting down into the endothelial area and going into the cells. So that illustrates the importance of your glycocalyx. You got to respect your glycocalyx, guys. Big time. So the other papers I have broadly, high sugar, standard American diets will do this. Hypertension and hypertension-related signaling molecules do this. Oxidative stress, sure, oxidized LDL, but not native LDL, interestingly. Smoking blows away your glycocalyx. That's one of the big problems with smoking. Arterial morphology. Atheroma and atherosclerotic plaques occur in very focal areas at branch points of arteries, and they've always been wondering why. One of the reasons is it looks like at those points they've been looking at the thickness of the glycocalyx, and it can be 60% or more thinner right at the branch points for reasons I won't get into. But there are papers now saying, hey, that's probably one of the reasons for the focal problem. And very briefly, ischemia reperfusion. When you do operations on people, you bring in oxygenation. And you can get rapid atherosclerosis in the segments that you've replaced, very rapid. And now there's papers tying that to the destroyed glycocalyx in the days and weeks following the operation is probably the major reason for what? For the accelerated atherosclerosis at those points, right? Is this important? Again, there's our target list. If you're doing all these things right, you know, you're going to have way less of this problem. Layer 2, the endothelium, gets a bit heavy here. So here's an endothelial cell, you know, happy camper, and here's the junction, tight junction with the next one, and they form a barrier. Here's your lumen, or the core of your artery, the red blood cells going by, and here's all your little happy LDLs, you know, bubbling around in your blood. I'll first go through endocytosis, because there were podcasts recently talking about this, and I wanted to clarify. Brown and Goldstein won Nobel Prizes. They discovered the LDL receptor. And endocytosis is when the cell, for its own needs, brings in an LDL cholesterol particle and breaks it up and takes its goodies out. That's for its own needs, not going across here into your artery wall, right? And in fact, a study quite some time back showed that when you increase the LDL concentration up here by 10 times, the endocytosis of LDL into the endothelial cells didn't even change, because the cell knows what it wants. It doesn't care what's outside, unless it's all gone, in which case you got a problem. So this is transcytosis, and I want people to focus now. Transcytosis is the process that actively manages taking LDL across the endothelial cell into the artery wall. Now, evolution is not an idiot, so it did this for a reason. You can argue about the reason. They have question marks because even in 2018, the top experts in this are acknowledging we're really not sure how this works. It's kind of embarrassing. So people have not been too interested in this for some reason. I leave people to guess why. So that's what happens. Here it is done with gold particles attached to LDL. Up here is the endothelial cell, and after a few minutes with LDL, with gold particles attached so they could track it, you see the little black dots of gold, right? The gold is brought in by the LDL into vacuoles, into the cell, within minutes. Within 20, 30 minutes, they're seeing LDL particles and their carried gold coming out, essentially in the intima, on the other side of the cell. So they're kind of like little Irish leprechauns, bringing their wee pots of gold across the endothelium. So, but I think, and you could make other jokes about LDL and gold, you know, as in how valuable LDL could be, but we won't get into that. So here they are. So that's demonstrated. In fact, 25% nearly off the LDL, and I think it was only a couple of hour period, had actually done the full journey. It was substantial. Nearly a quarter of it was out the other side, free, into your artery wall. So there. For transcytosis, which we're talking about, they did a 10 times higher LDL concentration up here, like I mentioned with the endo, and in fairness, it doubled the transcytosis. So 10 times LDL concentration, double the transcytosis. It's not a huge factor, you know, it's not 10 times. And for instance, in this experiment with TNF-alpha, an inflammatory component associated with insulin resistance, obesity, diabetes, it's a very active component in the body when it gets going. Using TNF-alpha introduced at physiologic levels brought up the transcytosis by 4.5 times by bringing in TNF-alpha. So you can see there's a lot of other things ruling transcytosis. And your brain, I heard it said recently that your brain doesn't take in LDL, it makes its own. Now it does make its own cholesterol mostly, but here's this paper. And essentially what they did was, they demonstrated LDL receptors in the blood-brain barrier taking in LDLs, transcytosing across the blood-brain barrier and into the brain for use. So evolution decided to do this. They also took the astrocytes from inside the brain cells, and they depleted them in cholesterol. They said, let's take the cholesterol out of them, and we do the experiment again and see, does the brain ask for more? That'd be cool. So they did it, and the brain did ask for more. The depleted astrocytes with lowered cholesterol upregulated the LDL receptors in the blood-brain barrier, and took through quite a lot more cholesterol. So this is really fascinating science. And it's your brain, which is important. So what kinds of things drive transcytosis? This is back to our million-dollar question. What things will make this go too fast, too much LDL? And there you have it. C-reactive protein, oxidized LDL, radical oxygen species, lipopolysaccharide from leaky gut demonstrated to do this. All these bad things that are essentially highly linked to our target list of important factors. Again. Last one, paracellular transport. Doesn't even end here. Paracellular transport is the leakage of LDL particles through the tight junctions between the endothelial cells and getting into your arterial wall. And you can have macropores too. There's tons of science on this out there. It's just hard to find. These tight junctions are exotic, 3 layers of ultra-exotic junctions to keep them tight, but they do break down and they do get damaged. So one thing again, TNF-alpha, inflammatory component. They introduced that and they got 4.5 times more permeability through this path, right? We saw it with transcytosis, also here. And the clever guys worked out the mechanism. They saw that the TNF-alpha was causing apoptosis, or cell death, of the endothelial cells. And as they died and turned over, they were opening up these junctions as they fluxed. And the apoptosis, or cell death, directly correlated with the amount of LDL going through, straight line. So they're really tying this together, you know. It's an exciting time for this science. What causes then this generally? We saw TNF-alpha, angiotensin II relating to blood pressure, and any insult to the endothelial cells is going to cause turnover and allow more LDL flux to occur, right? So you don't want to do that. How do you make sure you don't do that? Well, make sure you cover this list at the very least, right? No brainer. Last one, the intima proteoglycans, because there's still a layer, layer 3. So down here we have in the wall of your artery, here's your blood up here, LDLs that do get in can get trapped on these proteoglycan structures, and they get stuck there, they get oxidized, they get eaten by macrophage, and they get dealt with, right? So that's the way the body deals with them. But we'd be interested in what causes increased LDL reactivity and binding with these proteoglycans. What kind of factors make them bind a lot or bind not so much? That'd be important if you're worried about cholesterol. So here's the papers I have. Blood from heart attack patients, blood from insulin-resistant people, blood from type 2 diabetics. They all greatly increase, even with cholesterol standardized, greatly increase the binding down here. Small, dense, and oxidized LDL, especially with ApoC3 on board, which is a sign of insulin resistance, right? And small, dense is too, much higher affinity. Type 1 diabetic mice, I don't like mice experiments, but in this one, the diabetic mice with the same cholesterol levels as the wild type healthy mice, 8 times more cholesterol particles were getting bound in here from the diabetic mice. So these guys in these study groups are on the right track, right? They're looking to see what mediates the LDL particle being a problem. And unsurprisingly, you got a huge overlap with our classic target list of things not to do. So there you go, 1, 2, 3, 3 layers of evolutionary designed wonder, which will keep your LDL particles being happy if you do the right thing. And a set of very important factors that's common to nearly every part of this system becoming dysfunctional. And more, if you have obscure inflammatory conditions, it'll drive it too. It's not all these, but these are the big Pareto, the elephant. A bonus layer just when you thought you were going to get away. Small bonus layer, and I'm good on time. This is more recently I've been looking into oxidized LDL, and it's quite controversial, and I will have to warn you that this is kind of heretical. So you guys are going to be party to a heresy here. Now, I don't think they burn you alive anymore for that, but you might get, I don't know, an increased tax rate or something else. We'll see. So you're all here of your own free will. So here is a paper that's fascinating, and it's actually 1999, I think. Oh no, sorry, 2009. And there's a problem here. And the problem is that this guy or team who wrote this paper were quite clear on what causes atherosclerosis. They say that LDLs damaged in your blood through hyperglycemia or all the other stuff become problematic. They damage the endothelial, they damage the glycocalyx, they then come in, and in here they're a problem and the system tries to mop them up. But the problem with this paper is the heresy, because they are saying that native standard LDL, regardless of quantity, is not part of this. Now, the whole LDL hypothesis at its core, there's a crucial understanding. It is ordinary native LDL that gets in, gets oxidized, and causes the problem. So these guys are heretics, no question. But let's look to see that they have any studies that justify them. And this is a different team. And they took healthy controls and hypercholesterolemic patients. Now, they didn't have much data, but they had massive LDL, ratios were bad, and they were patients. So they picked people they figure probably had an issue. They took all their LDL, well, not all of it. They took a big sample of LDL, and they broke it up into different layers, L1 to L5. L1, L2, and L3 are not oxidized. They're not desialated. They're native healthy. And both groups had plenty of that. Uniquely, these guys had L4 and L5, which is very mildly oxidized and moderately oxidized. They're not completely destroyed. So they said, wow, now we've got a distinction between the healthy and the non-healthy. Let's see what it does. So they looked in an experiment at percentage cell death by introducing these particles, endothelial cell death. And they saw for L1 to L3 basically nothing. So okay, and when they put all three together and dumped it in, nothing. Nothing really happened. But then the L4 and L5, now you rocket up to 40% of the cells in the solution were killed, essentially. And they went further and they oxidized the bejesus out of LDL. They gave it a ruddy good kicking with copper. So they really oxidized it way more than L5. This is minimally oxidized, this is massive. But notice they didn't get much more result. So they said this minimally oxidized LDL we can measure in the blood appears to be a massive actor, right, in destroying endothelium, which will lead to all the other problems. And we know that this oxidized LDL measure, it's available, has massive odds ratios for future events. I mean, 4x generally, up to 17x if you mix it with some other problems, like bad ratios. So this OxDL measure is showing endothelial destruction, and we know it links enormously in epi studies to heart attacks. So you'd have to say, ooh, is the heresy true? Well, let's see. Let's look at some more heresy. Do you want a little more heresy and then we'll finish? Yeah. Everyone loves heresy, you know. So this separate team, 2017, bang up to date, Russian team of pathologists, cardiac researchers, and these guys are smart. I read this paper, went through it. They got healthy controls, type 1 diabetics and type 2 diabetics. They were looking at desylation, which is actually the step before the mild oxidation. And they're saying the oxidation is downstream. When the LDL begins to get desylated and begins to get a negative charge, it's already a big problem, even before it gets oxidized in your plasma. So they got the healthy controls and they did not have much of the desylated. The type 1 diabetic had a worse pattern and the type 2 diabetic was worse, which is kind of intuitive now from what we know. And they looked how much LDL would accumulate in the intima. They actually took intimal cells from people who were killed in car accidents. So they were healthy people otherwise. They took their intimal cells to make the culture. So this is really good, representing real life. And they saw that the non-desylated native LDL did very little in terms of getting LDL to accumulate in the intima, which is the big thing we want to know about. Then they looked at the desylated. Boom. So now you're seeing a hugely increased accumulation of LDL down in that wall based on the mild oxidation or desylation of the LDL. And again, this is happening in the plasma, in your blood, based on what you eat, based on what you do. It's not going into the wall and getting damaged. It's getting damaged in the blood and causing damage. That's what this would say. So we'd have to say there's quite a bit in this theory. It's not really heresy. To be honest, it looks to me like current science to be discussed openly and come to a consensus answer in coming years. But we'll see. We'll see if that happens. So layer 1, 2, 3, and we show that the big things you need to worry about mediate and govern a huge amount of all of these 3 layers of whether the LDLs being higher really transcends into a pathological problem. We've added layer 0 before any of this, which suggests possibly that the oxidizing and damage of the LDL in the blood is an initiating step. And if you avoid that, you may not even have to worry about this. But it's another LDL state measure that's not to do with the number of the particles. It's to do with the actual science. And heart attack patients in a recent paper had vastly more oxidized LDL than non-heart attack. I think non-heart attack people healthy had 0.1%, and the heart attack people had something like 5%. Like they just have tons more in the plasma. So it's important, and we'll need to answer these questions in the coming years. Always remember, are you on target? Because these things here aren't just helping you in many, many myriad ways. They're actually targeting the various layers that enable the high particle count to be a problem. So you're getting a double benefit by focusing on the right root causes, these and more, right? Now I'm going to close with, if your particle count shoots up on a diet, you cannot ignore something, and I showed you the hazard ratios earlier. That's clearly a hazard ratio marker. You can't ignore it, but you do need to take it in context. So for instance, there are ApoE4 genotype people. I'm one, my wife's one, David Bobbitt has one. We have a tendency towards heart disease and Alzheimer's. We respond much worse to modern foods and modern contaminants because we're the oldest genome. But some ApoE4s, there's evidence that if they become diabetic or damaged from standard American diet, and now they are diabetic, they have, in cases, a sensitivity to animal protein and fat in large amounts. So ironically, tragically, by damaging themselves, they now may be sensitive to some really good evolutionary foods. So it's kind of the corner case to watch for. Like if LDL shoots up and inflammatory markers shoot up as well and ratios shift to the negative, you got to watch it. But I think Dave will go through in much more detail tomorrow, is it, or this afternoon? Tomorrow, on all this LDLP and on a special class of people where the P goes really high, but generally all the other metrics stay good. So are they good and on target? We'll have to wait to find out. So that's it. Hopefully it helped.
Thank you, Ivor. So I wish that all our 3 speakers were playing for the Houston Astros because they have hit the ball out of the ballpark. That brings us to the next speaker. He